Okay, well, welcome back. So today we'll talk about side channels. So this is a topic we've alluded to, discussed briefly before, but we'll take a slightly deeper dive this time to look at some of the different types of side channels and types of attacks that have been demonstrated on different types of side channels. We won't get too deep into the technical details of how they work. That's a very interesting topic too, but we don't really have time to do justice to this topic at a real technical level. So there's actually a lot of so the side channel problem is partly caused by the fact that computers, especially small computers, are in all kinds of things, in every possible devices, embedded systems, RFID, sensor networks, IoT things. And because of that, devices are exposed to people and potentially attackers who might want to steal their secrets or do things, in all sorts of ways. Computers are no longer just mainframes hidden behind glass partitions with security guards, stuff like that. So there's, because there's a lot of ways devices are exposed to people and potentially attackers, including in the physical world, there's a lot of ways that kind of physical properties can be used in attacks, and that's what side channel is. Now, so the basic issue is, traditionally when we reason about a computing system, we tend to think of it in terms of there's an abstraction, a system represented by a hardware, software, and it takes inputs from the external world and it produces outputs, right? So we think in terms of these abstractions, and the abstractions are very useful in terms of allowing us to manage the complexity of designing and building systems. And so those are very important. But in terms of security, we're increasingly having to recognize that these abstractions are often problematic. They often hide things that are important for security, even if that hiding those physical properties was exactly the thing we wanted from a design perspective that can make design manageable. They can actually hide important things that can come back and bite us from a security perspective. And side channels often live in things like observable aspects of the physical world, the device's physical embodiment, such as voltage, timing, radiation, acoustics, optics, and things like that. So just some particular examples of potential sources of side channels: how much power a computer uses, how long it takes to do something, which areas of computer memory have been accessed at a certain point, and so on. So let's quickly take a deep dive into one common type of scenario where a side channel can be a big problem. So one of the most important and broad areas are timing attacks, and this is a big topic in research as well as in practice in security practice. So many crypto systems execute code that whose natural, easiest to program implementation executes conditionally based on information that might be secret or in part secret, such as the parts of the private key. And the natural ways to code these algorithms, such as RSA and DSA, and many of these cryptographic algorithms that we talked about earlier in the course, can create, within the execution, the process of executing one of these functions can take different amounts of time to execute, depending on, say, whether a bit of the private key is a 0 bit or a 1 bit, right? And so anybody who can somehow observe the execution timing of the code, even if they can't directly observe the 0 or 1 bit that's being computed on, if they can observe how long the different parts of the code takes, can potentially read that information. And so let's and so this is often a passive attack. The attacker doesn't have to change. The attacker isn't changing anything in the computation that's being performed. The attacker is just passively observing somehow. And there's many potential ways an attacker can do that. So let's look at a particular case, the classic RSA public key square and multiply algorithm. So this is used in RSA encryption and decryption. The natural, and this is actually the first time in this course that we're in some sense opening the black box of these cryptographic primitives. For most of this course, I've been treating cryptographic primitives as just abstractions. And normally, unless you're actually designing and building cryptographic primitives, normally that's a good way to think about them. But when we're looking at side channels, we now have to open up the black box and see how they work. And so the natural way to implement RSA modular exponentiation through square and multiply is basically to iterate over the bits of the secret. So the secret is D. So we first initialize the result X to some constant C, and then we iterate over the bits of input D. J goes from 1 to n, the number of bits, and then and then we look at whether that secret bit is either 1 or 0. If it's a 1, in either case we square, do a modular square of the value x. That's the value we'll conditionally multiply in. In either case, we'll square it, but only if the secret input bit is a 1, then we'll additionally multiply it by C, right? And so this is just a standard natural way to do modular exponentiation by D, by this secret input D. Now, so you should be able to see where the potential problem is. If we're just squaring, squaring is going to take less time than squaring and multiplying, right? And so we'll come back to ways that might be observed. But if that can be observed by an attacker, then that leaks information about it basically leaks the entire private key. So let's look at another example how timing exacts can occur. If you enter your password or anything else on the keyboard, and an attacker can just overhear the timing of your keystrokes. They're somewhere in the room, or they have a microphone somewhere in the room that can hear tap 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 tap. You can't. Presumably, you shouldn't be able to get a lot of information from just those taps, but some clever researchers discovered that you can actually get statistically, with some statistical probability, a surprising amount of information just measuring the timing differences, timing variations between how long between each key press. So if you're and this is likely somewhat specific to a given person, but especially if they know the habits of a particular person or have some data, each of us has a particular, kind of pattern and habits. And, statistically, it's possible to learn information about, which combinations of keys you're likely pressing just by analyzing the differences between the timings of your key press. And this is an attack that's been demonstrated. So I won't get into the more technical details. Here's a third case of timing attack that's been demonstrated. But through it's timing related, but through a different channel. And we'll start looking at a particular channel. So the AES encryption algorithm, as part of its operation, you have to take 256-bit or 8-bit inputs and then basically look them up into a table. Look them up in a table, transform them into some output for which it's possible to compute the outputs, but in practice it's easiest just to do a 256 entry table lookup, right? And so this is a very natural way to implement AES. The problem is the index you're using in those table lookups tends to be secret inputs, like the 1 byte of the secret key that goes into the AES cipher. And so if an attacker can somehow observe which entry of the table you're looking up, then the attacker can, then that leaks 8 bits worth of potentially secret key to the attacker, which is naturally really bad. So how does the attacker actually observe the timing in this attack? Well, there's various ways that an attacker might, but the classic way that this kind of attack works is through memory. So assume we're in a cloud environment, or we're in a multi-user desktop environment where a victim process is running AES, running SSH or TLS or something, and this process is doing a lot of AES operations, encryption and decryption operations in the context of TLS or SSH, and then there's an attacker-controlled process also running on the same system that doesn't have access, can't directly break into the victim's process, can't directly affect anything, but can context switch back and forth quickly, or even potentially run concurrently on a different core or on a different hyperthread context, right? So the attacker, and actually Intel's hyperthreading tends to make a lot of these problems worse because it becomes very, an attacker can get kind of very fine-grained concurrency with the victim and can sometimes exploit these channels at a very fine-grained and high bandwidth fashion. But this general kind of attack works in many contexts. It's just how quickly and how effectively it is in a different context. So the basic idea is what the attacker is going to do. The attacker knows how the AES software is linked and loaded in the victim's process, and this is fairly common. This is actually a fairly realistic assumption because most of these binaries are standard. They come on a standard distribution, and so this isn't that hard for the attacker to guess. And there's other ways the attacker can use side channels to figure out the layout and general behavior of a victim's process, even if the attacker doesn't automatically have all that information. So let's assume the attacker knows the set of memory locations that this AES table is stored in, and the attacker also knows the architecture of the cache that this is running on, that the victim's thing is running on. In particular, the attacker knows the attacker has his own memory pages, and he knows he has some page that he can write to or read from that he knows will hit the same cache lines as the victims, right? He won't be able to actually read the victim's data or anything because the hardware is going to keep the cache lines separate to the processes, but the attacker can write data such that it'll evict the victim's cache lines, right? So the attacker is, knows that the victim is going to run AES, so the attacker goes and writes just attacker's data into the attacker-controlled pages in such a way that the attacker knows it's going to flush out the victim's most or all of the AES table entries from the victim's process, right? And then the attacker just waits. Maybe the attacker context switch to the victim, kind of yields to the victim process, or just waits until he guesses or knows the victim process will run. And so the victim process runs its AES code, and that AES code load, does memory loads from one or more entries of that table, right? And whenever the AES code loads from a table, it's going to, because the AES table has been evicted from the cache, those are going to be cache misses, and it's going to load the evict the attacker's data from the cache now and load the AES table data back into the cache for those particular table entries that got hit, right, by the AES code. So, okay, so that has changed the cache state. Now, finally, at some point after, when some AES loops happen, the attacker gets control again. Again, either because of another context switch or because the attacker was continuously running and it just stopped waiting. And so now the attacker wants to figure out, okay, which of these AES table entries got accessed by the victim. So the attacker, can't directly read the state of the cache, but what he can do is try to read back the attacker's data, right? And he'll read a particular entry, and if that read is fast, then that means, kind of below a threshold in time, then that probably means that the victim's AES code did not load from that particular cache line. Whereas if it's much slower, and these differences are fairly huge because of the memory hierarchy, then the attacker can infer that the AES encryption loop did load from that particular cache line, right? So now you're probably, so this is, as you might guess, this doesn't give, completely break the AES private key, all in one go. The attacker is getting probably pretty fuzzy, noisy information here. Several of these, cache, if you're familiar with the, cache architectures, these table entries aren't usually, conveniently exactly one cache line in size for the attacker. So some of the table entries are likely to land on the same cache line, and the attacker won't be able to distinguish some of them. And multiple iterations of the AES loop might run before the attacker comes back and gets any information, and this kind of thing. There's there's a lot of ways that limit the amount of information the attacker gets in practice from any given iteration. But on the other hand, especially in the side channel attack community, we have very sophisticated ways that the attackers can statistically analyze from many, many, many runs. So in practice, the way these attacks work is the attacker, knows that the victim is doing a lot of AES encryption or decryption, all using the same private key, And this is very common, you know, and often even the attacker can cause that to happen by opening a long-running TLS connection and, like, you know, download, you know, open a TLS connection, download a bazillion, you know, bytes of data that, you know, the attacker knows that you know, the victim is going to be encrypting or decrypting repeatedly. And then the attacker does these kinds of operations over and over and over. And you know, each information sample is going to provide very little certainty. You know, kind of is going to be very noisy and provide very little certainty. But by, you know, averaging and accumulating this information statistically over, you know, millions or billions of runs, the attacker can very quickly derive enough of the enough bits, you know, reasonable certainty about enough bits of the key, so then the attacker can just kind of brute force search for any remaining bits that they didn't get from this attack, right? So, for example, if the attacker never gets certain bits, like, you know, attacker never gets the low 2 bits or something because all of the adjacent 2 or 4 or whatever table entries are always in the same cache line, so, you know, kind of the attacker can't get the low bits that way. But, you know, that's okay. The attacker doesn't need those low bits because, you know, if the attacker can get most of the other bits, then, you know, just brute force the last 2 bits or the last few bits, right? So that's, you know, kind of to illustrate how these kinds of attacks work and why, you know, even if the attacker is getting, you know, pretty noisy, bad information at a pretty low, unreliable bit rate, and not even getting all the bits necessarily, still, you know, if the attacker uses that capability, that leakage intelligently, that's often enough to completely break cryptographic systems after enough tries. Does this make sense? You know, questions about that? So here's another example. So, you know, similar to the AES attack, but going back to RSA. So, you know, this kind of attack has been demonstrated in the case of RSA using, you know, I mentioned how with the standard, you know, square and multiply loop, if the attacker can sense that, then you know, then the private key leaks. Well, this is one particular way, you know, using cache flush and reload to allow the attacker to sense what the victim is doing. So the attacker process basically flushes the cache, waits, reloads the information, and then goes and reads the cache, reads the timing, you know, checks the timings of all these cache reads to basically determine, you know, the attacker isn't necessarily learning any specific, you know, bits from what the victim is doing, but only trying to determine how much progress the victim made, you know, since the attacker last took a sample. Right? And just that information, just how much progress the victim has made, you know, in a known code path since the last sample, can be a devastating timing attack. At least if the victim code is not, you know, is not properly hardened against these kinds of timing attacks. In particular, it's become standard practice to write cryptographic code with constant time operations, which is a pain. But, you know, this kind of attack will not be effective if the cryptographic code is written so that it always takes the same amount of time to execute independent of what the secret input is. But that hasn't been the standard practice until recently. And so even being able to use, say, a cache flush and reload type observation just to monitor how quickly or slowly some victim code, say RSA code, proceeds in its known code path can quickly reveal the private keys. Okay. So what can we do about these? So I mentioned. So there's a variety of ways to address these attacks. One way is just to try to calculate things in a way that the code never depends on the execution path, or execution time never depends on the data, the actual content of the data. Now this is often, sometimes this is easy, but often it's a real pain. Especially for public key type operations on big numbers and stuff, because big numbers are always usually big, but they're not always the same size. Some randomly picked big numbers have more 0 bits on the left side than others, and internally they're often normalized so that if one big number is 1 byte or 1 word shorter than another, then it'll store, use less memory to store the shorter big number. This is just kind of a natural optimization. It's how you would write a big number library if you were, kind of a sensible software engineer mostly, right? But because of that, multiplying big numbers or adding, doing anything with these variable size numbers can leak timing information, because suddenly the amount of time it takes to add or multiply or do anything with these big numbers depends on how many bits they actually have, how many non-zero bits they have and stuff. So that can be a timing leak. So we can do things like avoiding conditional branches on secret information. So often we have to reformulate code paths, like this example I provided, to avoid those conditional branches. So if that bit of d equals 1, then square it. We want to compute the same thing, but without actually doing a conditional branch. Can anybody guess, how might you recode this particular loop, this RSA loop, to be constant time? So it doesn't, so that the execution timing will never depend on the value of d sub j, while still computing that same thing. Any ideas? Well, yeah.
I think you just make another else, and you can compute on the else the modulus, which actually takes the most time, but you don't make the assignment. So
so you add an else, and you.
Or just make the modulus there, but then you just don't make the assignment on the else side. So you actually make the same computation.
Yep. So that's absolutely. So that's the starting point. So the mod x times c, that's the multiply step in the square and multiply loop. We want to execute that regardless of whether d sub j is 0 or 1. So we're going to move that out of the if statement and just compute x primed equals mod of x times c comma n, big N, right? So we're going to create a value x prime, compute this value that we might or might not need depending on the value of that secret bit, but we're going to compute it anyway regardless, right? So making code constant time, this is a first important point. Making code constant time often amounts to making it slower. We are intentionally de-optimizing the code, because from a pure I want the code to run as fast as possible perspective, you would never do this. You would always prefer just to compute what you need to compute. But writing constant time code means you have to do exactly the opposite. You have to always compute everything you might need just in case you need it, even if half of the time or most of the time you won't you'll just discard it, right? Yeah, so that's the first thing you would do. You would move the x prime, say x prime equals mod xc comma n outside of the if statement. And then you could stop there. You could just leave the if statement there and say, if d sub j equals 1, then x equals x prime. Right? You could just say, okay, I'm still going to have the if statement, but I'm going to do just a very small assignment statement there. And you would kind of be most of the way to constant time execution, and that might mostly eliminate the attack, because in this case, the mod xc comma n is a big, heavy operation. That takes a lot of time, and a simple assignment of x equals x prime, that's going to be a tiny, minuscule amount of actual time. So you're replacing a big time difference, a big obvious time difference, with a much smaller time difference. That's already good, a good step from a timing hardening perspective, but it's not ideal because we've kind of learned over and over that even surprisingly small, minute timing variations are still measurable, and the attackers can still get in statistical information. Yeah, it makes it harder, slower to build it for the attacker to build up the information they need, but it's still possible, still doable. So you wouldn't really want to stop there. So what could we do then? So we've moved we're doing the multiply regardless, and now we have these two values x and x prime. We want to pick one of them. We want to either just keep x if d sub j is 0, or use x prime if d sub j is 1. But we want to do that in constant time. How might you? Can you think of a really constant time way of coding that? Let's say x and x prime are byte arrays or something. Yeah. Right. Yeah.
So you can also have the if else. If it's okay, we make the assignment, and else we just make another assignment like x prime equals x.
Yeah. So the problem is you still got an if else. And if you have any if-else at all, then that's going to mean there's a branch, and there's some code that only executes in one case, and some other code that only executes in the other case. And even if the difference is minute in terms of execution time, even if they're running almost exactly the same instructions, just the fact that the else clause instructions might be on a different cache line, instruction cache line, as the if clause instructions might be on a different cache line than the else clause instructions, that might be something that the attacker can again detect through a timing attack. So we really want, kind of to succeed, we got to completely eliminate all if-else conditions that depend on secret data like d sub j. Can you think of a way to do that? Yes?
We can compute d times x prime plus 1 minus d times x.
Bingo, good. So you come up with some arithmetic calculation exactly like that, and it can be, binary arithmetic or integer arithmetic, whatever. And you just, calculate that. So one of the standard ways to do this is to take the value of d sub j, turn it into a mask by say, negating it. So it's either 0 or FFFFFFF, for however big you want. And then you compute the two things you want, like, x sub 0 is one value, x sub 1, or, x prime is the other thing. And then you iterate through the variable, taking, each word of x is x sub 0 and the mask value, or x prime, the x prime word and the opposite of the bitwise complement of the mask. So there's various ways to do that, but basically you have to come up with an arithmetic equivalent of the of the condition, so that you're always computing the same thing, never using a branch, but you ultimately get the result, right? Yeah, so good call. And as you can guess, have any of you actually written constant time code out of curiosity? Have you seen my constant time code? Okay. So yeah, it's not fun. It's a royal pain, and you're deliberately de-optimizing code. Constant time always runs slower, like I mentioned. But it's one of those things we gotta learn to do, at least when we're writing crypto these days. Okay. So yeah, so doing that kind of thing, coding sensitive data, sensitive operations defensively, using constant time and stuff, is becoming more and more standard practice, at least when dealing with cryptographic code. Another type of defense we can use is to just make it harder to observe, for an attacker to observe the timing. For example, if we can, in this kind of case where the only if we're on a single core processor that only runs one process at a time, and the attacker has to contact, and kind of the attacker and victim have to contact switch back and forth, and only one runs at a time, then we can effectively limit the amount of information, the effectiveness of these kinds of timing attacks by introducing delays to when the attacker gets preempted, when the attacker gets rescheduled, and things like that. Basically make it really hard for the attacker to tell time at a sufficiently accurate level to learn to judge, for example, whether a cache line was evicted or not. Now, that kind of approach can work in some cases, but it's in most operating systems, most environments, it's actually pretty hard to close down all of a potential attacker's ability to get fine-grained timing information. And that's partly because of concurrency. Most of our machines are now multi-core machines. Most process environments are multi-threaded, and if the attacker can just, even if the attacker doesn't have a good timing, the attacker can create a thread that just loops endlessly, incrementing a counter, and that can basically substitute for a high resolution timer. So yeah, so closing down avenues for exploiting timing channel leaks is not easy. Okay. So that's timing channel. The timing channel issue is one of the most commonly exploited, and also often seen as one of the most serious, in part because that's timing channels are really the only ones that sometimes work remotely, say over the internet. And it's actually been shown, of course, it's much more difficult if you're talking to a server over the internet, to get sufficiently precise timing information about what the server is doing and stuff like that. But it has been shown feasible in certain limited circumstances that some of these timing attacks can even work remotely over quite long distances, but only when in the right conditions. Most other side channel attacks really assume and require that an attacker has to have some presence physically close to the victim device or victim process. But that's, and you know, so that's an important assumption. So, you know, kind of just keeping so this means, you know, for most side channel attacks, physical security mechanisms work pretty well. If you can, you know, lock the sensitive stuff in a room, put a guard in front of it, and, you know, kind of make sure nobody bad gets in, you know, hopefully that will protect against, you know, most side channel attacks, you know, is similar to the way it protects, hopefully protects against physical attacks, with some important exceptions. But because devices are so pervasive and we have an increasingly number of, you know, kind of security critical devices that people carry around with them, IoT devices and stuff, these other attacks, other types of side channels are becoming more and more important as well. So power attacks. Every circuit tends to, you know, every electronic circuit consumes power, and that the amount of power it takes tends to depend on what it's computing, which instructions the processor is running at a particular moment, you know, how it's accessing memory, the pattern in which it's accessing memory, whether it's getting cache hits or cache misses when it's accessing memory, all kinds of stuff like that. Accidentally, you know, everything that a chip does is basically accidentally broadcast upstream in the form of its power consumption. Right? So if you can, so in principle, if an attacker can watch with sufficient precision how and when, you know, the waveform with which a device consumes power, the attacker can actually get a lot of information. Right? So, of course, this typically, you know, actually doing this typically requires fairly detailed knowledge of the device and its implementation. But often that's, you know, that can be either available or, you know, attackers tend to get really good at reverse engineering many types of devices. And it, you know, depends on how much patience and time the attacker is willing to invest in analyzing the device. But so this was a classic experiment where, you know, triple deaths. This was the standard symmetric encryption algorithm before AES came out, basically, and that was vulnerable to side channel attacks too. In particular, you could look, you know, attacking a particular hardware implementation of triple DES as it goes through the bits of the private key or processing, doing its standard process. You could literally read off the waveform, you know, that's a 1 bit, that's a 1 bit, there's a 0 bit, you know, so. So you could just read that directly off the waveform with the right type of analysis. Back to our old friend RSA. So we've you know, brought it up several times. Like I said, you know, kind of if you have that vulnerable square and multiply loop, well, the cache is only one of many timing channels through which that information might leak. So, you know, if you have a physical device that's implementing that vulnerable square and multiply loop, and you can't necessarily directly, you know, see the loop going, but you can, the multiply and square actually takes more power than just the plain square part, and this was observed in one of these experiments. And then, so you could see on an oscilloscope waveform that, yeah, you know, the square and multiplies are these big blobs of effort, and, you know, simple multiplies are these little blobs, and it's, you know, totally obvious, basically. It's totally trivial to read the bits of the private key off that kind of analysis. Yeah. So Now, like I said, there's many variants of these side channel attacks, and they've been getting more and more sophisticated. So differential power analysis is a more advanced statistical approach to analyzing power to potentially exploit timing channels. So the basic idea is so, you know, as you might expect, it's not always this easy, you know, to exploit side channels, but in many cases when it's not that easy, approaches like differential power analysis can succeed. For example, so kind of the standard way it works is by having the attacker gets to watch many encryption operations, but then basically chooses a guess of a key or a partial key, and then gets to run to observe a bunch of different traces using that guess, and gets to see, well, how good was my guess? Was it, you know, was I a little bit correct or not at all correct or a little bit more correct? And again, you know, the attacker doesn't need to get a lot of information from each run for the attack to succeed. And so this is the kind of way that these differences can be revealed. For example, if you're so the power reference versus a sample where you got a particular bit correct versus you got you guessed incorrectly, well, you know, that can show up. Okay, so I won't get into the details, but this is a very powerful technique, in part because in principle it can be used to break pretty much any algorithm. But in practice, there's ways to defend against it. For example, by reducing the signal size, introducing noise, things like that. And increasingly, hardware designers have to, especially designers of cryptographic hardware, have to care about these types of things. Okay, so. Yeah, so that's probably a good time to take a break. Let's take a break until 5:10.